Two numbers. Same universe. Different answers. About 67. About 74. Two values, both for how fast space itself is stretching, both calculated by some of the most careful astronomers alive, both refusing to agree with each other. For years, the field assumed one of the numbers had a quiet error inside it. Wrong calibration. Stellar crowding. Some hidden bias the next generation of instruments would clean up. The James Webb Space Telescope was the next generation. It cleaned almost everything. The numbers still do not match. You'll see why one method reads the universe's baby photo and the other reads its current body, and why both should describe the same cosmos but no longer do. You'll meet the galaxy that reset the most distant record, glowing only 290 million years after the Big Bang, brighter than any model predicted. And you'll hear a Nobel laureate say plainly that what is left, when every error has been ruled out, is the possibility that we have misunderstood the universe itself. We start there. Before we go further, if you find yourself settling into these long, slow walks through cosmology, a quick like or subscribe makes a real difference for the channel. It is a small thing on your end. It is a much bigger thing on mine. Now, let's begin. There's a number physicists have spent 100 years trying to pin down. It has a quiet name, the Hubble constant. It describes how fast space itself is expanding, how quickly the distance between any two distant galaxies is stretching, simply because the universe between them is growing. The number has a unit that sounds technical, but the meaning is simple. It is written as kilometers per second per megaparsec. A megaparsec is a fixed distance, about 3.26 million light years. So the unit just means, for every 3.26 million light years between you and a galaxy, the universe adds that many kilometers per second of recession. The bigger the number, the faster the cosmos is expanding. For decades, that number was a single value, with shrinking uncertainty bars around it. Two methods of measuring it agreed, within their errors. Cosmology felt finished, in the way a long-built bridge feels finished, even if the engineers know there is always one more bolt to check. Then the bolts started loosening. By the early 2000s, two independent ways of measuring the Hubble constant began drifting apart. By the 2010s, the drift had become a gap. By the 2020s, the gap had passed the threshold physicists treat as the end of polite debate. Two numbers. Same universe. Different answers. About 67 kilometers per second per megaparsec when measured one way. About 73 to 74 when measured the other way. A 9% difference. In a science where the error bars are now down to about 1%, a 9% difference is not a smudge on the page. It is a wall. The man who has been pressing on that wall the hardest is named Adam Riess. He shared the 2011 Nobel Prize in Physics with Saul Perlmutter and Brian Schmidt. Their joint discovery in 1998 was that the expansion of the universe is not slowing down, the way gravity should be making it slow. It is speeding up. The thing pushing the universe outward, against gravity's pull, was given a placeholder name, dark energy. It is still a placeholder. We have not yet learned what it is. Riess won the Nobel for finding that we did not understand part of the universe. Decades later, leading a team called SH0ES, he found something else. The way the universe expanded just after the Big Bang, predicted from the oldest light we can see, says the Hubble constant should be near 67 today. The way the universe is expanding right now, measured from galaxies we can map directly, says it is near 73 to 74. Both methods are good. Both have been duplicated, replicated, refined, double-checked. Both have had their error bars squeezed down by an order of magnitude over the last 20 years. And as their precision has improved, the gap between them has not closed. It has widened. In 2024, Riess and his collaborators published a paper that closed off the last comfortable explanation. Using the James Webb Space Telescope, they measured 1,000 of the special stars used to set the local distance scale, all the way out to a galaxy called NGC 5468, about 130 million light-years away. The point of the exercise was to look for the hidden error that everyone hoped was hiding in the Hubble Space Telescope's older measurements. Stellar crowding, calibration bias, something Webb sharper I would catch and fix. Webb confirmed the older numbers. The error was not there. And in a NASA statement accompanying the publication, Adam Riess wrote a sentence that should not appear in finished physics. With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe. A Nobel laureate, a man whose career has been measuring the expansion of space, a man who built his name being more careful than anyone else, who fought for years to keep the door of measurement error open, watched it close, and said, in plain language, that we may have misunderstood our own cosmos. That is what the title means. That is the different universe. It is not a different universe in the sense of another reality somewhere else. It is the universe we're sitting inside, right now, this second. The same cosmos that is holding your room together, holding the air on Earth, holding the stars in their orbits. It is just a universe whose rules, when read out from one corner, do not quite match the rules read out from another. And the better the instruments get, the louder the disagreement becomes. This is not a story about competing crackpot theories or fringe science. The two teams that produce the disagreeing numbers are not on the margins of cosmology. They are at its center. The Planck collaboration is the most careful satellite project ever built for cosmic microwave background measurement, with hundreds of scientists across Europe and beyond. The SH0ES team is among the most experienced groups in the world at the cosmic distance ladder. Both have published in the most peer-reviewed journals. Both have had their analyses checked, replicated, and tested by independent teams. There's no reasonable scenario in which one of these groups is sloppy. There's no reasonable scenario in which the other is biased. They are doing careful, well-documented science. And they are getting different answers. The Hubble tension, as it is now called, has become the most uncomfortable open problem in modern cosmology. To understand why a 9% gap can rattle a field that prides itself on being right to 1%, we have to look at what those two numbers actually are, what each method is doing, why each one should match. And it is not a small disagreement. To see why the disagreement matters, we have to start with the older of the two numbers, the 67, where it comes from, what it is reading. It comes from the universe's baby photo. Imagine, for a moment, the cosmos as a child. Imagine you have detailed measurements of that child's body at the age of 2. Their bone structure, their growth rate, their family genetics. From those numbers, a careful pediatrician can predict, with reasonable confidence, the child's adult height. Not exactly, but close, within an inch or two. That is what the lower Hubble number is doing. It is the prediction, made from the cosmos's earliest baby photo, of what the expansion rate should be today. The baby photo has a name, the cosmic microwave background. About 380,000 years after the Big Bang, the universe finally cooled enough for light to travel freely for the first time. Before that moment, space was so dense and so hot that photons could not move more than a tiny distance without being absorbed and re-emitted. The universe was a glowing fog. Then, in a relatively short stretch of cosmic time, atoms formed, the fog cleared, and the photons that had been bouncing around inside it streamed out in every direction at once. Those photons are still here. They have been traveling for 13.8 billion years. The expansion of space has stretched them, redshifted them, taken light that started in the visible range and pulled it down into long microwave wavelengths. They fill the sky. Every cubic meter of the universe is lightly bathed in that ancient light. In the room around you, right now, photons that left the universe's first transparent moment are passing through your body, your walls, your skin. They have been traveling, undisturbed, for almost the entire age of the cosmos. They arrive now. The cosmic microwave background is, in literal terms, the oldest thing it is possible to see. Older than every galaxy. Older than every star. Older than every atom that was ever assembled by gravity into something larger. A satellite called Planck, named after the physicist Max Planck, was launched in 2009 by the European Space Agency. Its job was to measure that ancient light to extraordinary precision. Across years of observation, Planck mapped tiny temperature variations across the sky. The differences are minute, on the order of 1 part in 100,000, but they carry an immense amount of information. The pattern of those variations encodes, in a measurable way, the contents of the early universe. How much ordinary matter there was. How much dark matter. How much dark energy. how fast the universe was expanding when the photons last bounced. Planck was not the first satellite to do this work. NASA had sent up an earlier satellite called WMAP in 2001, which produced the first detailed maps of the cosmic microwave background and gave the field its first precision values for the age of the universe and for the proportions of its contents. Before WMAP, an even earlier satellite called COBE, in the early 1990s, had detected the temperature variations at all. The progression has been steady. COBE found the lumps. WMAP measured them. Planck refined them to a precision that, for many of the basic parameters of the universe, has since closed off most of the remaining room for ambiguity. From those numbers, with the standard model of cosmology, called lambda CDM, you can run the calculation forward. You can ask the model to grow that early universe up, the way the pediatrician grows the 2-year-old up. Apply the physics, add the gravity, stretch the space, account for the dark matter scaffolding, the ordinary atoms forming galaxies, the dark energy starting to dominate around 5 billion years ago. Run it forward, all the way to today. The model gives an answer. The expansion rate today should be about 67 kilometers per second per megaparsec. Give or take a small uncertainty. That is the prediction, from the baby photo. Plus the rules of physics we believe we understand. The universe should be expanding at about 67. It is one of the most carefully constructed predictions in science. The Planck data has been reanalyzed by several independent teams. Other ground-based experiments, like the Atacama Cosmology Telescope and the South Pole Telescope, have measured the same ancient light using different instruments. They agree. The number is solid. That is half of the disagreement. The other half is not a prediction. It is a measurement, a direct reading of the universe as it is right now, taken not by deriving the value from a model, but by going outside, looking up, and asking the cosmos directly. To do that, you need a way to measure cosmic distance. And the woman who made cosmic distance possible was, when she did the work, sitting at a wooden desk in the Harvard College Observatory, examining glass photographic plates by hand. Her name was Henrietta Leavitt. She worked at Harvard in the late 1800s and early 1900s, in a group of women hired to do tedious astronomical calculations. They were called computers. The men did the observing and the publishing. The women, paid less, did the math. Leavitt was assigned a stack of photographic plates of a small galaxy near our own, called the Small Magellanic Cloud. Her job was to identify and catalog variable stars, stars that brightened and dimmed in regular cycles. There were thousands of them. She went through the plates, plate by plate, star by star. In a particular subset of variable stars, called Cepheids, she noticed something. The brighter Cepheids took longer to complete their light cycle. The dimmer ones cycled faster. The relationship was not a vague tendency. It was a smooth mathematical curve. The longer the period, the brighter the star. That single observation, published in 1908 and refined in 1912, gave astronomy its first reliable cosmic ruler. Here's why. If two Cepheid variables have the same period, they have the same intrinsic brightness. So if you find a Cepheid in a distant galaxy, measure its period, and compare its apparent brightness to a closer Cepheid of the same period, the difference tells you how far away the distant one is. Closer stars look brighter. Farther stars look dimmer. The geometry is exact. Leavitt's discovery was the bottom rung of what astronomers now call the cosmic distance ladder. Each rung uses a kind of object whose brightness can be calibrated. The closer rungs are calibrated against direct geometric measurements. The next rungs use Cepheids, calibrated against the closer ones. The next rung above Cepheids uses a particular kind of supernova, called a Type 1a, calibrated against galaxies whose distance is known from Cepheids. Type 1a supernovae are extraordinary tools. They are the deaths of certain white dwarf stars in binary systems, which explode at almost identical brightness when they reach a critical mass. They are bright enough to be seen halfway across the visible universe, and because they all explode at almost the same intrinsic brightness, they make excellent standard candles. Find one. Measure how bright it appears. Compare to its known intrinsic brightness. The difference gives you the distance. The story of the Hubble constant has its own quiet history of disagreement. Edwin Hubble himself when he first measured the recession of distant galaxies in 1929, derived a value of about 500 kilometers per second per megaparsec. That value was wildly off, by a factor of 7, because his calibration of the Cepheid distance scale was incomplete. As the century progressed, two competing camps emerged. One, led by the astronomer Alan Sandage, argued for a value near 50. The other, led by Gerard de Vaucouleurs, argued for around 100. The disagreement was so stubborn for so long that an entire generation of astronomers worked under the assumption that the Hubble constant might be either of those values, and the cosmology that fell out of each was very different. The Hubble Space Telescope Key project, completed in 2001 by a team led by Wendy Friedman, finally settled that older dispute, placing the value near 72. That, for a brief moment, looked like the end of the story. The team that has refined this latter more than any other is called SH0ES, which stands for supernova H0, for the equation of state of dark energy. Adam Riess leads it. The team has spent 20 years measuring the local Hubble constant by climbing rung after rung, geometry to nearby Cepheids, nearby Cepheids to more distant Cepheids, distant Cepheids in galaxies that have hosted Type 1a supernovae, Type 1a supernovae out into the smooth cosmic flow, where the universe's expansion dominates the motion, and what they get, after all the calibration, all the cross-checking, all the careful uncertainty propagation, is a number, about 73 to 74 kilometers per second per megaparsec. That is the local Hubble constant, the same physical quantity that the cosmic microwave background prediction places near 67. For a long time, the field assumed that one of these numbers contained a buried mistake. It is the natural assumption. The two methods are doing wildly different things. Reading ancient light versus climbing a ladder of nearby stars. Of course, one of them might be miscalibrated. Of course, there might be an error somewhere in the chain. The error would be found, the methods would converge, and the universe would settle back into a single agreed value. That assumption held through the early years of the discrepancy. As the gap widened from 1 sigma to 2, then to 3, the most natural reading was that the systematics were not yet under control. Stellar crowding could affect Cepheid brightness. Type 1a supernovae might have small environmental dependencies. The cosmic microwave background analysis itself might have hidden assumptions that, once unpicked, would shift the prediction towards 73. For 2 decades, every refinement, every new dataset, every additional check was supposed to bring the two values closer. Instead, both numbers got more precise, and the gap stayed. By the end of the 2010s, the disagreement had grown to a level of statistical significance that physicists treat as a turning point. In particle physics, the conventional threshold for a confirmed result is 5 sigma. That means the chance of the result being a fluke is about 1 in 3.5 million. By 2019, the Hubble tension had crossed 3 sigma. By the early 2020s, it had passed 5. Adam Riess, in a recent interview, said the gap is now near 6, and possibly 6.5. A 2 sigma curiosity is something a careful scientist might politely ignore. A 3 sigma result is interesting. A 5 sigma result is, in physicists' vocabulary, the line between, do not bother me with that, and, this does not make sense. The Hubble tension crossed that line. Both methods are right. Both numbers are real. They simply disagree. When two careful methods, measuring the same thing, disagree at 5 or 6 sigma, the field has a vocabulary for what comes next. It does not say, we have a tension. It says, we have a problem. And when the problem refuses to dissolve under more data, more checks, more independent analyses, the vocabulary changes again. A 2 sigma result, in 2010 or 2011, would not have alarmed anyone. The early measurements from the Hubble Space Telescope, when they first started showing a tension, had error bars wide enough that it could have been noise. By 2016, the gap was hovering around 3 sigma. By 2018, it had crossed 4. By 2019, the Hubble Space Telescope's most careful analysis put it past 5. The cosmic microwave background measurements, on the other side, were also getting more precise. The Planck satellite ended its data collection in 2013, and the final analyses, published in 2018 and 2020, locked the prediction near 67. Both numbers settled. Neither moved toward the other. There is something almost stubborn about the way the two values held their ground. Each new dataset, each new analysis, each new check should have moved one toward the other. None did. The Cepheid measurements grew more precise. The cosmic microwave background measurements grew more precise. The two numbers, holding their separate places, simply became more sharply separated. The error bars closed in around them like brackets. They did not overlap. In 2019, at a conference held at the Kavli Institute for Theoretical Physics in California, a Nobel laureate named David Gross stood up and said something that made the cosmologists in the room uncomfortable. He said the Hubble tension was no longer a tension. He called it a crisis. The word stuck. Not officially, not in textbooks, but quietly. In the corridors and in the seminar rooms, the cosmologists who had been calling it a tension started calling it something heavier. A few years later, in conversation with Scientific American, the physicist Dan Skolnick of Duke University said the same thing in plainer English. We have been at this Hubble tension level for a long time. At some point, the community needs to say, this is more serious. The step up from tension is crisis. The reason for the change of word was simple. A tension is a thing you can resolve with more work. A crisis is a thing where the framework itself might be wrong. For most of cosmology's modern history, the framework has gone by a single name, lambda CDM. The lambda is the symbol used for dark energy, the unknown thing pushing the cosmos apart. The CDM stands for cold dark matter, the second unknown thing whose gravity holds galaxies and clusters together. Together, they make up about 95% of the universe's mass and energy budget. The remaining 5% is the part we know how to touch and measure, the atoms and stars and planets and bodies. Lambda CDM has been astonishingly successful. It explains the patterns in the cosmic microwave background. It explains how galaxies cluster across the sky. It explains the abundances of the lightest chemical elements, made in the first 3 minutes of cosmic time. It explains, to high precision, the way the universe has expanded across 13.8 billion years. What it does not explain is the disagreement at its heart. Take the Planck team's measurement of the cosmic microwave background. Apply the lambda CDM model. Run it forward. The model gives the prediction near 67. Then take the SH0ES team's local measurement, climbed rung by rung. Compare. The numbers do not match. The framework is the meeting point between the two answers. So if both answers are correct, the framework, somewhere inside, must be incomplete. That is what crisis meant in Gross's mouth. It is not that cosmology is collapsing. It is not that the Big Bang did not happen, or that the universe is younger than 13.8 billion years, or that any of the well-measured pieces of the model are about to be thrown away. The pieces are too well tested. The cosmic microwave background is real. The expansion of space is real. The general framework is well anchored, but the model that ties the two ends together has a missing piece. Something between the early universe, where lambda CDM predicts 67, and the current universe, where direct measurement gives 73 to 74. Something we do not yet know how to write down. For a long time, the most reasonable hope was that the missing piece would turn out to be a measurement error after all. A subtle systematic in the Cepheid ladder. A hidden bias in the Planck analysis. Something that, once found, would close the gap and put the field back to sleep. That hope is now mostly gone. It is mostly gone because of one thing. A new telescope was supposed to settle this. It made it harder. Quick break. If the science is finding its way into your night, a like or a quiet subscribe helps the channel stay slow and patient like this. Small thing on your side, bigger thing on mine. Now, back to the telescope that was supposed to make the tension go away, and instead made it worse. The James Webb Space Telescope launched on December 25, 2021, on an Ariane 5 rocket from French Guiana. After its long unfolding in space, it parked itself at a gravitationally stable point about 1 million miles from Earth, called the second Lagrange point. From there, with its 18 gold-coated hexagonal mirrors and its enormous tennis court-sized sun shield, it became the most sensitive infrared eye humanity has ever built. Among the many things Webb was supposed to do, one was to sharpen the bottom of the cosmic distance ladder. The reasoning was straightforward. The Hubble Space Telescope, although extraordinary, has been operating for over 30 years. Its mirror is 2.4 meters across. Webb's mirror is 6.5 meters across. Webb sees infrared light far better, and infrared light is exactly what you need when you are trying to pick out individual Cepheid variable stars in distant galaxies, where the visible light is dimmed by interstellar dust. Webb's sharper, redder eye should, in principle, find Cepheids that Hubble could only see as smudges. It should pick them out cleanly from the background, free of the stellar crowding that some critics had blamed for the local Hubble constant being biased upward. If the local number was wrong because of stellar crowding, Webb would prove it. Webb would remeasure those same Cepheids, this time without crowding, and find a lower value, closer to 67. The tension would shrink. The field would breathe. The first Webb measurements arrived in 2023. They were preliminary, but already telling. The Cepheid measurements held. The local Hubble constant, when retrieved from Webb's data, sat near where Hubble had placed it. Then, in 2024, a team led by Adam Riess published a paper that closed the case. Their paper appeared in the astrophysical journal Letters in February of that year. The team had used Webb to observe roughly 1,000 Cepheid variables across 5 host galaxies of Type 1a supernovae. They reached out as far as a galaxy called NGC 5468, about 130 million light-years away. NGC 5468 is the most distant galaxy where Cepheids have been clearly identified and measured. It marks the end of the second rung of the cosmic distance ladder. Across the entire range Hubble had measured, Webb remeasured. Same stars, different telescope, different decade. The values agreed. Stellar crowding, the most popular candidate for a hidden error, did not show up in Webb's data. The crowding effect, if it existed, would have made Hubble's measurements artificially brighter, biasing the local Hubble constant upward. With Webb, free of that crowding, the local value should have come down. It did not. In Riess's words, the team had spanned the whole range of what Hubble observed, and could now rule out a measurement error as the cause of the Hubble tension with very high confidence. That sentence was the death of the easy escape. It is hard to overstate how much hope had been pinned on Webb. For a decade, when astronomers asked each other privately how the Hubble tension would resolve, the most common answer was, Webb will fix it. Webb did not fix it. Webb, the most careful, most expensive, most refined infrared telescope ever placed in space, confirmed the disagreement. That confirmation did something subtle inside the cosmology community. Up until that point, it was still respectable to say, in private, that the tension was probably a systematic effect, that one of the numbers was about 10% off due to a subtle bias somewhere in the Cepheid chain, and that future data would settle it. Webb made that position much harder to hold. The chain had been rebuilt with new instruments, by independent calibrations, using sharper images. The number stayed where it was. Some hope remains in alternative tools. The tip of the red giant branch method, which uses a different class of stars to set distances, has produced values intermediate between 67 and 73, though most recent analyses lean closer to 73. The Carnegie Hubble program, led by a different team, is using Webb to refine its own version of the local measurement. Several upcoming surveys, with the Nancy Grace Roman Space Telescope and ESA's Euclid mission, will add more independent rungs. Wendy Friedman, the astronomer who led the Hubble Space Telescope key project that settled the original dispute back in 2001, has spent the last decade championing this red giant branch method as a check on the Cepheid scale. As stars age, they pass through a stage where their cores ignite helium fusion abruptly, in a flash, and the resulting brightness ceiling is sharp and predictable. Across many galaxies, the brightest red giants reach almost the same intrinsic luminosity. That gives a separate rung in the distance ladder, independent of Cepheids, calibrated through a different physical process. Her early measurements, using Webb data, sat closer to 70 than to 73. More recent measurements have moved upward. The current Carnegie Hubble program value remains slightly lower than the SH0ES value, but its uncertainty bars overlap. Friedman herself has said publicly that the tension may be smaller than the loudest version of the story suggests, but it is not zero. The two methods, Cepheid and red giant branch, are different enough that they catch different systematics, and both are now firmly above the Planck prediction. But the simple version of the escape, the version where Hubble had a hidden error and Webb would catch it, is closed. There is no place left to hide. It was after that paper that Adam Riess wrote the line. He wrote it as part of a NASA statement accompanying the publication. It is a careful sentence, written by a careful man. Read it slowly. With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe. Let me say that again, because the first time you hear it, it does not quite sound like physics. We have misunderstood the universe. That is not a press release sentence. That is not a phrase someone reaches for to make a popular article more dramatic. That is a Nobel laureate, who has spent his career being more cautious than almost anyone in cosmology, writing in plain English what he believes the data is now showing. He does not say it carelessly. He does not say it for effect. He says it because the alternative he and his team spent 15 years pursuing with everything they had, was that the local Hubble constant was wrong. That was the comfortable alternative. They could not find it. The James Webb Space Telescope, which was supposed to help them find it, did not. So what is left, Riess writes, is the real possibility that the model itself, the framework we use to translate the early universe into the present universe, is not complete. That is what the title of this video means. A different universe. Not in the sense of a parallel reality. Not in any mystical sense. The universe is the same one we have always lived in. The galaxies are the same galaxies. The stars are the same stars. The atoms in your hand have not been rearranged. None of that changes. What changes is the description. For most of the 20th century, cosmology built a remarkable map. The map said the universe began in a hot, dense state about 13.8 billion years ago. It expanded, cooled, made the lightest atoms in the first 3 minutes, then sat in darkness for hundreds of millions of years until gravity gathered the first matter into the first stars. Galaxies formed. Heavier elements were forged inside stars and scattered when those stars died. Eventually, planets formed. Eventually, on at least one planet, atoms became chemistry. Chemistry became biology, and biology became an animal capable of asking how the whole thing began. The map worked. It explained the cosmic microwave background. It explained the patterns of galaxy clustering. It explained the proportions of hydrogen and helium and lithium across the cosmos. It even predicted, in the late 1990s, that the expansion of the universe should be slowing, until Riess's own group, along with Saul Perlmutter's, found that it was speeding up instead. That single observation forced the addition of dark energy to the map, and the map kept working. But now there is a place where the map disagrees with itself. The map says the universe today should be expanding at about 67. The actual universe is expanding at about 73 to 74. Same map, same universe. Two answers that the map cannot reconcile. What that means, in the most literal sense, is that the map is missing something. There's at least one piece of physics, somewhere between the cosmic microwave background and now, that we have not yet written down. Something acted between the universe's first transparent light and the present moment that the model does not include. Whatever that thing is, it would have changed the way the universe expanded over time, in a way that pushes the local value up, or the early prediction down, or both. We do not know what it is. Adam Riess's recent statement is not the panic of someone who suspects cosmology is collapsing. He is not predicting the end of the standard model. He is saying, in plain language, that the standard model has a hole in it. The hole is real. The hole is large enough to push two of cosmology's most carefully measured numbers 9% apart, and the hole has resisted every easy attempt to fill it. This is the moment at which a Nobel laureate, after a long career of careful measurement, says we may have misunderstood the universe, not as a slogan, as a working description of where the field stands. The closest historical parallel is probably the late 19th century, when classical physics seemed nearly complete, and a small handful of unresolved problems, the constancy of the speed of light, the spectrum of blackbody radiation, were waiting in the corner. Within a few decades, those problems opened the door to relativity and quantum mechanics, and physics turned out to be much stranger and much richer than the late Victorians had imagined. Cosmology may, or may not, be in a similar moment now. We do not know. Some of the people who will write the next chapter are likely working today on graduate degrees, watching the data, waiting for the cleaner signal that will tell them which direction to push. It is one of the strangest places modern physics has been in a long time. The Hubble tension is the loudest crack in the model. It is not the only one. The cosmic microwave background and the Cepheid ladder are not the only places where the standard story is starting to creak. There is also a handful of things the James Webb Space Telescope has been finding, almost from its first deep field, that the model did not expect. The most famous of them is a small reddish smudge in a stretch of sky near the constellation Fornax. It is too faint for the human eye to detect by any means. In a Webb image of nearly empty sky, it appears as a tiny, slightly fuzzy patch in a cosmic forest of distant galaxies. It has a name that is unromantic but precise: JADES-GS-Z14-0. JADE stands for the James Webb Advanced Deep Extragalactic Survey, one of the largest programs Webb has run. GS marks the field of sky, called the Good South Field, where the smudge sits. The Z14 is the important part. It is the redshift, the number telling you how far back in time the galaxy is. In October 2023, and again in January 2024, Webb's Near-Infrared Spectrograph, NIR-SPEC, stared at this particular galaxy for almost 10 hours of integrated observation time. The spectrum that came back was unambiguous. JADES-GS-Z14-0 is at a redshift of 14.32. Before this object, the previous record holder for most distant spectroscopically confirmed galaxy was a slightly less extreme object called JADES-GS-13-0, sitting at a redshift of 13.2 and dating from about 400 million years after the Big Bang. The new record pushed that boundary inward by another 100 million years of cosmic time. A redshift of 14 means that the wavelengths of the galaxy's light have been stretched by a factor of about 15 between when they were emitted and when they reached Webb's detectors. The cosmos has expanded between then and now by that much. Translating that redshift into time, using the standard cosmology, gives a single startling number. The light we are seeing left the galaxy when the universe was about 290 million years old. The current age of the universe is 13.8 billion years. So this galaxy's light has been traveling for almost the entire age of the cosmos, and it dates from a slim window of time, not long after the cosmic dawn, when the first stars were beginning to ignite. 290 million years out of 13.8 billion. Roughly 2% of cosmic history. That alone makes JADES-GS-Z14-0 the most distant galaxy ever spectroscopically confirmed. But what the team measured next is what made the cosmologists sit up. The galaxy is bright. Surprisingly bright. Its rest frame ultraviolet absolute magnitude is about -20.81, which is comparable to a moderately luminous galaxy in the present universe. Webb measured it to be over 1,600 light-years across. To make that size feel real, imagine the Milky Way, which is roughly 100,000 light-years across in its visible disk. JADES-GS-Z14-0 is about 1/60th of that diameter. That sounds small, but it is enormous for an object that has had less than 300 million years to gather itself, light up, and start producing stars at a serious rate. Most early universe models, run forward from initial conditions, were producing galaxies at this redshift that were a fraction of that size and a small fraction of that brightness. In other words, this galaxy is large, not Milky Way large, not Andromeda large, but for an object that has had less than 300 million years to assemble itself out of hydrogen and dark matter, it is large. A common worry, when distant bright galaxies are reported, is that they might not be galaxies at all. Quasars, which are the bright cores of galaxies powered by supermassive black holes, can produce enormous luminosities from very small volumes. If JADES-GS-Z14-0 were powered by a quasar, the light could be coming from a region not much bigger than our solar system, magnified by 1,000 times by the gravitational pull of a central black hole. That would explain the brightness, without requiring the galaxy itself to be unusually big. But the team's measurements of the size ruled that out. The light extends over more than 1,000 light-years. A black hole's accretion disk is much smaller. The light has to be coming from young stars, distributed across a galactic scale. A separate team, using the mid-infrared instrument on Webb, called MIRI, also detected the galaxy at a longer wavelength of 7.7 microns. That detection is important. It picks up emission from the galaxy at wavelengths that, in the rest frame, correspond to ionized gas signatures. The detection helps confirm that what Webb is seeing is light from young, hot stars heating their surrounding gas, not light from some other process. Stefano Carniani, an astronomer with the Scuola Normale Superiore in Italy and a member of the JADES team, said the obvious thing afterward. "It is stunning," he said, "that the universe can make such a galaxy in only 300 million years. It is the kind of thing the standard model did not predict." In the textbook version, the first galaxies should have been small, faint clumps of hot young stars, slowly accumulating mass as gas collapsed into dark matter halos, slowly building up structure over hundreds of millions of years. The early universe should have been dim by our standards, populated by infants. Galaxies the size and brightness of JADES-GS-Z14-0 should not appear so soon. And then more of them showed up. In one of the first Webb deep field images, released in the summer of 2022, a Dutch astronomer named Ivo Lab and his collaborators found a population of distant galaxy candidates that, by their initial photometric measurements, looked unusually massive, not just bright, like JADES-GS-Z14-0, but massive. The implied stellar masses, when fit to standard galaxy templates, came out around 10 billion solar masses, at redshifts of 7 to 8 or higher, where the universe was less than a billion years old. Lab and his collaborators published the result in 2023 in the journal Nature. Independently, another paper, by Michael Boylan-Culkin at the University of Texas at Austin, ran the numbers theoretically and made an unsettling point. The amount of stellar mass implied by Webb's measurements at those redshifts was at the very edge of what lambda CDM can physically allow. To make galaxies that massive that early, you would need essentially every available baryon, every available proton and electron and neutron in a dark matter halo to convert into stars. Real galaxies, observed locally, convert only a few percent. Webb's early candidates were implying, depending on the analysis, 50 to 100%. Boylan-Culkin's paper put it carefully. The most massive Webb candidates lay at the very edge of lambda CDM's physical limits, indicating an unresolved issue with either the inferred properties of the galaxies or with lambda CDM itself. It was as if someone had pointed a flashlight at a corner of cosmology that everyone assumed was solidly mapped and seen the floor sag. But this is the part of the story where careful science gets careful. It is one thing to find a single galaxy, like JADES-GS-Z14-0, whose redshift is confirmed by spectrum, whose size is measured directly, whose brightness is unambiguous. It is another thing to claim the existence of a whole population of unusually massive early galaxies, based on photometric estimates of their stellar mass alone. Stellar masses, derived from the way light is distributed across different infrared filters, depend on assumptions. Assumptions about the kinds of stars present, about how much dust is mixed in with the gas, about whether what looks like an old, massive starlight glow is actually an old, massive starlight glow, or whether it is a younger galaxy with strong emission lines from hot ionized gas, mimicking the same colors at much lower mass. In 2023, a follow-up study using a different Webb survey, called Canucks, reported that several of the previously flagged ultramassive candidates, when looked at more closely, were not extreme at all. They were star-forming galaxies whose red colors came from emission lines, not from old massive stellar populations. The team concluded that the early excitement might have come from sample bias and cosmic variance more than from a real failure of lambda CDM. Other papers have followed. Some have argued that simulations always predicted plenty of bright early galaxies, and the apparent tension came from comparing observations to too restrictive a theoretical baseline. Others have argued that systematic uncertainties in stellar mass estimation can swing the apparent excess by an order of magnitude. A recent analysis from late 2025 took the systematic seriously and found that, once amplified Eddington bias is properly handled, much of the apparent tension shrinks toward consistency with the standard picture. There are now several major Webb surveys looking at this same regime. JADES is one. Two others, called SOURCE and UNCOVER, are independently scanning different patches of sky for high redshift galaxy candidates. Each survey has produced its own list of strange early objects. Each has produced its own corrections after follow-up spectroscopy. The picture is slowly clarifying, although not in any single direction. Some of the early candidates have been spectroscopically confirmed at the redshifts originally claimed. Others have shifted, sometimes significantly, when better data arrived. So where does that leave the story? It leaves it in an honest, layered place. JADES-GS-Z14-0 is real. The galaxy exists. The redshift is confirmed by spectrum. The brightness is measured. The size is measured. It is a luminous, well-structured galaxy 290 million years after the Big Bang, and the simplest models of early galaxy formation did not expect to find it. Other measurements from the same Webb spectrum have refined the picture further. The galaxy's ultraviolet continuum, the slope of its light across short wavelengths, is unusually steep. The observed slope, called beta, is around -2.2, almost as blue as a young stellar population can be. That fits a galaxy that is still in its first burst of vigorous star formation, with very little dust accumulated to redden its light. The combination, very young, very bright, very early, is what the team meant when they called it the archetype of a kind of galaxy that nobody quite knew the universe could make. The broader claim that there is a whole population of impossibly massive galaxies challenging lambda CDM is much less settled. Some of the original candidates have shrunk under careful analysis. Some have not. The literature is still debating which is which, and how much of the apparent tension survives the corrections. Some of the strangeness was bookkeeping. Some of it was not. What remains, after the corrections, is a population of early galaxies that look brighter and form faster than the simplest theoretical models had expected. Not so much as to break lambda CDM, but enough that careful theorists are quietly proposing that something about early galaxy formation, or possibly about the early expansion of the universe, may be different from what we wrote down. This is where the two anomalies start to point in the same direction. The Hubble tension between the early universe prediction of 67 and the local measurement of 73 to 74 requires something between then and now that is not in the standard model. Either the early universe expanded a little faster than lambda CDM allows, or the late universe expanded a little slower, or some combination. Whatever the missing piece is, it has to bridge a 9% gap. The early massive galaxies, if their excess is real, also require something between then and now that helps gravity gather material more quickly than the basic model expected. Either dark matter clumped earlier than we thought, or galaxies converted gas into stars more efficiently in the early epochs, or some additional source of energy or pressure changed the balance. Both anomalies live in roughly the same region of cosmic time, the first few 100 million years after the Big Bang. Both anomalies tug at the model in roughly the same direction. The question theorists are now asking is whether one piece of new physics, added to lambda CDM, could explain both at once. There are several candidates. None has won. The most discussed is called early dark energy. The idea is that, around the time the cosmic microwave background was emitted, there was a brief episode when the universe contained an extra component of dark energy that decayed away. That brief extra push would have made the early universe expand a little faster than the standard model assumes. When you then run the calculation forward to today, the implied modern expansion rate comes out higher, closer to 73. Early dark energy was originally proposed to ease the Hubble tension. Some recent papers argue that the same model, by speeding up early expansion, could also let galaxies form somewhat earlier than the standard picture predicts. That would help with the early massive galaxies problem, although the magnitude is still being studied. The early dark energy idea was given its modern form around 2018 by a young theorist named Vivian Poulin and his collaborators. The model has been refined since then, tested against multiple datasets, and adjusted in detail. The current generation of early dark energy models can match the cosmic microwave background and the local Hubble constant simultaneously, which is exactly what lambda CDM cannot do. The cost is the introduction of a new field with new parameters that turned on briefly in the early universe and turned off again. That cost is what the field is debating. Another candidate is some form of evolving dark energy, where the dark energy component changes over time rather than staying constant. If dark energy was stronger in the past or weaker, the inferred expansion rates from the cosmic microwave background and from local measurements would shift. Recent results from the Dark Energy Spectroscopic Instrument, called DESI, hint that dark energy may not be exactly constant. The data is preliminary. The interpretation is contested, but it is enough to keep the idea alive. DESI began releasing its first cosmological results in 2024 and 2025. Its analysis of the way galaxy clustering has changed across cosmic time hinted that the dark energy equation of state, the parameter that describes how dark energy behaves, may not be exactly the value lambda CDM assigns it. The deviations are small, around 2 to 3 sigma in the early analyses. They are not yet at the level where the field is convinced, but they are notable enough that several leading cosmologists have started talking about them seriously. If the DESI hint holds up under further data, dark energy may turn out to be a slightly more complicated thing than this simple cosmological constant. That, by itself, would be a major result, with or without the Hubble tension. A third candidate is a modification of gravity itself. The argument is that general relativity, which we use everywhere in cosmology, might need a small correction at the largest scales. Such corrections are constrained by many other tests, but there are versions that could, in principle, account for the tension without breaking other parts of the model. They are typically considered a last resort, since changing gravity is a bigger move than adding new fields. A fourth candidate is some unknown property of dark matter or some additional dark sector physics. New particles, new interactions, things that influence cosmic structure formation in ways not captured by treating dark matter as simple cold weakly interacting matter. None of these candidates has cleanly won the field. Each one fits some data and breaks others. Early dark energy, when added to fit the Hubble tension, can introduce small disagreements with galaxy surveys. Modified gravity solutions tend to run afoul of solar system tests. Dark sector physics is so flexible that it can fit almost anything but predicts almost nothing specific. The honest description of the field is this: there are several plausible directions in which the standard model might be incomplete. The data is not yet sharp enough to choose between them. Several upcoming surveys, from Euclid to Roman to LSSD to next-generation cosmic microwave background experiments, will produce data over the next 5 to 10 years that should distinguish between these possibilities, or rule them out, or suggest something else entirely. The Hubble tension is the strongest single piece of evidence that something is missing. The early Webb galaxies, when stripped of their bookkeeping noise, are a quieter second piece of evidence, pulling in roughly the same direction. The various candidate fixes are, at the moment, hypotheses being patiently tested. Cosmology has been here before. In the late 1990s, when the data first showed that the universe was expanding faster than expected, the field could have refused to accept it. Instead, after careful confirmation, dark energy was added to the model, and the model kept working. Adam Riess won a Nobel Prize for that. The current tension might require another adjustment of the same kind. It might require something stranger. We do not yet know which leaves one quiet question. What does it mean, then, for a Nobel laureate to look at the universe and say we have misunderstood it? It does not mean the universe has changed. The cosmos that surrounds your room tonight is exactly the cosmos that surrounded it last week, last year, 10,000 years ago. The galaxies are in their places. The stars are turning. The cosmic microwave background is still bathing the room with photons that left the early universe almost 14 billion years ago. None of those facts is in question. What has changed is our description, or, more carefully, our awareness that the description has at least one place where it does not fit. For most of the last century, the description fit beautifully. The Big Bang model, the expansion, the cosmic microwave background, the formation of galaxies, the proportions of the chemical elements. Decade by decade, measurement by measurement, the description got tighter. It became one of the great achievements of human thought, a model of the entire cosmos, anchored to data derived from physics. It is still that. The recent tensions do not undo any of it, but they remind the field of something easy to forget. The model is a description. It is not the universe. It is the human framework we have placed around the universe in order to think about it clearly. And like every framework that has ever been built around a piece of nature, this one too has edges. There are places where it fits well, places where it fits less well, and places, increasingly, where it does not fit at all. The Hubble tension is one of those places. The early Webb galaxies, in the parts that survive careful scrutiny, are another. When Adam Riess writes that we may have misunderstood the universe, he is not saying the universe is unknowable. He is saying our current description has a missing chapter. The chapter has not yet been written. Whatever it contains, it will be what physicists and astronomers spend the next 20 years working to find. Some of those people are alive today. Some are still in school. Some have not yet been born. There is something quietly hopeful about that. The story is not finished. The tools are still sharpening. The data is still arriving. And the universe, in its old patient way, keeps offering new things to find on a timetable that ignores ours. The reason the disagreement matters, even on a quiet night, even in a small room, is that it tells you something about how science actually works. Not as a finished textbook, not as a settled set of facts, as an ongoing conversation between human instruments and a universe that always carries one more layer than the last description captured. The universe is not different from how it really is. It is different from how we wrote it down. We were not wrong about the cosmos. We were wrong about being finished with it. And the cracks in the model are how the next century of science will breathe. The next time you look at the night sky from a window or a porch, what you are seeing is exactly what the standard model describes. Stars and their patterns, galaxies, where they are bright enough, drifting in their slow recession, the faint glow of the Milky Way overhead, light that has been traveling for years or thousands or millions of years to reach your eyes. You are also seeing, in a sense, the field that the model fits, the same field that is now tugging at the model from two different ends, asking gently to be redescribed. None of the strangeness is anywhere far away. It is in the same sky you have always known, the same expansion that pulls every distant galaxy outward, the same baby photo of ancient light that fills the room around you. You have not been lied to about any of it. You are simply living in a universe whose physics is not yet completely known. That is not a frightening thought. It is the oldest thought in science. The universe holds. The model is unfinished. And tonight that is enough. Good night. If you stayed with us through this slow walk, through one of the most uncomfortable problems in modern cosmology, the channel grows when you take a quiet second to like, subscribe, or leave a comment with the part that stayed with you. It is a small action on your end. It is a real signal on mine. Sleep well, and the next time the night sky is up there, I'll be there with another one of these.